Greg, are you ready?
Yep.
Okay, let's start. Hello, good morning, good afternoon, and good evening, and welcome again to this World River and the Delta System Source to Sink webinar series. This is Paul Liu from NC State University. So this talk series is co-sponsored by NSF, NC State, Louisiana State University, and East China Normal, and Utrecht, and the CSDMS. So today is our great honor to invite the Dr. Greg Smeato from University of St. Andrews come here talk about the role of middle latitude sedimentary system in the global carbon cycle. So before I introduce Dr. Smeato, I want to mention again all our previous talk, including this talk, will be and have already been archived on our YouTube channel. So there are more than 100 talks over there. Please use it, take advantage of these great resources for your research and education. At the same time, we also maintain a Source to Sink Twitter account. As you can see, we will announce all the weekly talks, the webinar series, the information. So you are welcome to follow us. At the same time, next week, next Wednesday, we will have Professor John Shang from University of Arkansas come here talk about distributory channel networks connecting form and function. And remember, United States will start summer saving time this coming Sunday. It's March 13. So next week, we still have a United States East Coast 9 a.m. But next week will be London, UK 1 p.m., Paris 2 p.m., and Beijing 9 p.m. This is very good news for our Chinese colleague. I'm very sorry, many our talk in the winter time is 10 p.m. There are still many students and colleagues coming up here. So for starting from next week, so our Chinese colleague, the talk will be 9 p.m. That's very good news. Then Europe after March 27, London and Paris will shift back to 2 p.m. and 3 p.m. So I don't know why US and Europe or UK cannot coordinate the summer saving time. It's very confused, you know. So, but anyway, at least we are now in a one village together online. So, okay, Greg Smeato is a research fellow, University of St. Andrews. As you can see, he graduated originally from University of Edinburgh and also get a master of University of Dundee, and then PhD in St. Andrews in the marine geoscience. His research mainly focused on understanding the role of the marine and intertidal sedimentary environment in the global carbon cycle in different environments. So, coastal carbon is very important, particularly in middle latitude, and his research currently focused on the salt marsh of the UK and the continental shelf sediment is northeast Atlantic, particularly focused on the Fjord sediment. So, Greg, thank you very much for coming here, give a talk. Please go ahead to share your screen. Yeah, it looks good.
Okay, thanks for inviting me for this, to give this talk. As Paul says, I basically work on sediments in the mid-latitudes. The mid-latitudes have largely been ignored for the more shiny science that can be done in the Arctic and tropical regions. So the mid-latitudes are quite open to some of this research. So the questions I work on are: how much carbon is held in these coastal and shelf sediments? How is it spatially distributed? How quickly do these carbon stores form? And where does the carbon come from? So is it terrestrial, marine, or some other source? So I'll be discussing most of this in a UK context, or around the UK at least. And I'll also be discussing some other ongoing work about the reactivity of the carbon in relation to anthropogenic disturbance, which is a hot topic at the moment, Fjord-Shelf Connectivity, and the age of the carbon, like how old is the carbon in these systems. So the couple of those last things will be at the end of the talk, where it's just it's more of a, here's what I'm doing, more than here's the actual answers I've come up with. So marine sedimentary environments. So globally, most of the seabed is abyssal plain. And when it comes to carbon, there's not much carbon there, and it forms fairly slowly. So what we're really focused on is the continental shelves and the slopes. So in this simplified version, the white and yellow bit. And around the UK has quite a lot of this. But globally, there has been a few attempts at understanding the carbon stocks. Currently, this one by Lee is the best one. It only focuses on the top 5 centimeters, and they basically use machine learning processes to estimate that about 87 gigatons of organic carbon, plus or minus essentially 50%, is stored in the top 5 centimeters of sediment globally. At the moment, I think this is the best one. There is another one floating around, but that focuses on the top meter, which is ambitious to come up with this one, since a lot of the cores weren't a meter long. So they estimate there's about 2,322 gigatons in the top 1 meter of sediment globally. But as you see from their data set, it's quite interesting, since, as far as I know, marine sediments with a bulk density above 2.5 is basically rock. And if you find a marine sediment with 60% carbon, something's went horribly wrong. So in the data set they've used for this includes blue carbon environments, so intertidal, and it skews the actual stocks. The next important part is how quickly does this carbon build up in these systems? So over the years, Hedges and Keogh, and this data that was summarized in the Smith et al. Paper in Nature Geosciences basically comes up with a number of about 175 million tons of carbon each year is buried in marine sediments. Most of this in continental shelf sediments and some more offshore. And when you normalize it, fjords come out as a big hotspot for carbon storage, and continental shelves are the second, but still a lot lower than fjords. So these are the two areas I'll really be talking about today, fjords and continental shelves. So I think these global estimates are as good as they're going to get at the moment. What we really need is more localized studies to understand the processes and what's going on at a regional scale. Then what we know from the regional scale can be upscaled. So I'll focus in on the UK sedimentary environments. So this is the UK exclusive economic zone. It's largely a passive margin that includes fjords, continental shelves, and estuarine environments. And during the pandemic, we did a desktop study, basically pulled together every piece of data we could get, and we calculated the top 10 centimeters of sediment in the EEZ stores about 262 plus or minus 68 million tons of carbon, organic carbon, and another 1,290 megatons of inorganic carbon. And within the Scottish waters, so basically the top bit is what Scotland manages, most of the carbon stored in this area. You can see that the big hotspots for carbon are basically the fjord areas, the muddy patches in between the islands, and the major estuaries around the UK. So when it comes to burial in these sediments, it's a lot more difficult to understand. There's far less data. So in the mid-90s, the Haas estimated that about 100,000 tons of organic carbon was buried in the North Sea. So the area shown in this map, probably that area. And what they actually showed was a lot of places there's not much sedimentation or none at all. And this recent work by Marcus Deasing shows that shows three zones in the North Sea. There's basically the Norwegian Trench that is burying a lot of carbon, which is not a surprise. The blue area, which is active as stuff is burying, but getting buried, but it's very slow. And the green, where basically nothing's happening. And of course, there is another area missing from this, the sediments that are being eroded, but actually modeling something you cannot measure is difficult. So yeah, basically North Sea, about 100,000 tons of organic carbon a year, which is an important number when we start to compare the inshore waters to. So what I'm really interested in, or what I've done most of my research so far in, is with hotspots for this organic carbon burial. And in Scotland, that's fjords. So globally, Smith et al. In 2015 estimated about 18 million tons of organic carbon each year is buried in fjords. And this was up to between 21 and 31 megatons by Schwie in 2016. And when normalized for area, more OC is stored in fjords than any other sedimentary environment. So they are truly hotspots for carbon burial. And when you look at the map of fjords around the world, Scotland is highlighted as a place we have fjords. We call them sea lochs, but they are essentially fjords. So yeah, Scotland's fjords. We have 133 large fjords, which are the classical fjord. Glacially over deepened with sills at the sills within and sills at the edge, blocking stopping outward flow. Some of these sills are not as large as you witness in New Zealand or Chile or even northern Norway, but they are still there. We also have 115 small fjords, which many would consider actual fjords. So these are in Shetland and the Outer Hebrides. So this is the Outer Hebrides, this is Shetland in the bottom corner of the map. These systems are flat bottomed and tend to not have sills, so they're more like flooded estuaries than classical fjords. So they are slightly different. And overall, about 2,608 kilometers squared of Scotland's coastline is fjords. So it makes up the whole west coast of Scotland, basically. So the first question we have to ask is how much carbon is stored in these sediments? Before we have to even think about anything else, just how much is there? So when I started my PhD, I came up with a methodology using seismic geophysics to create grids of sediment volumes across basically all the sea lochs that had seismics. So that was these ones here. And these are an example of one of these seismic profiles. So the two blue colors are post-glacial sediments. So sediments deposited since the ice retreated in this area, about 13,500 years ago. The green is younger dryas deposits, so when the ice re-advanced. And then the orange stuff is material that was deposited while the last glacial ice sheet retreated. So we did this to all of these fjords. We went and got long cores that most went into all the way through the post-glacial, and a couple went into the glacial material. So we had data from all these layers. And basically, we took the volumes and the data from the cores and calculated carbon stocks for these. So you can see here that, for example, the post-glacial sediments in Loch Suna store 9.4 megatons of organic carbon. So the real question is, we've got 5 of these. Can we get a number for the whole of Scotland? So we threw in every variable we could find for the catchments, the tidal regimes, the rainfall, the weather in all these catchments of fjords. I put them into a cluster analysis, and 4 clusters fell out. So the orange, group 1, is the classical fjord. The group 2 is still mainly mainland and would still be considered a fjord, maybe less silled. Group 3 is the islands, so these fjords, and group 4 are weird ones. So there's 2 of these. Loch Linnhe, the big one, which is the biggest fjord in Scotland. It's probably, in reality, the top is a fjord and the bottom is more of a bay. And Loch Eriboll, which is the only permanently hypoxic fjord in Scotland. So that makes sense. And basically, when you look at where the greatest amount of ice was during the last glaciation, it basically falls on top of the orange fjords. So they're more over deepened with glacial features than the green ones. So it does make sense. So, and luckily, the 5 fjords we got depth integrated stocks for fall into these categories, with the exception of group 3 ions. So we upscaled using this, basically took a standard carbon density and applied it across the area. We calculated that about 252 million tons of carbon is stored in the post-glacial sediments of Scottish fjords. And when you look at the distribution of this, more like 30% of it is held within 2 fjords, Loch Fyne and Loch Linnhe. These are the 2 biggest fjords, so it's not a surprise. With basically 200 megatons held between them. The top plot, the frequency diagram, shows that there's a lot of fjords with a lot of small fjords with not much carbon in it, and a few big ones with a lot, and that's how it's distributed, which makes sense. So once we had a rough stock of the sediment, we really wanted to know how the carbon was actually distributed within these fjords. This is one of the big questions. There's a lot of assumptions that these places are full of mud, and it's just mud. And if you want to start to think about upscaling burial rates or things like that, actually knowing what the sediment type is and how much carbon's there is an important thing. So we looked at existing data sets. So the first one here is the BGS substrate type map, and the second one is a European product called from EmoNet, which is basically a simplified version of the BGS. And you can see that none of the fjords are actually touched. It doesn't actually go into any of them. So basically, at this point, we have no clue what sediments are inside fjords. There's a few ways we went around getting around this. So we thought, what data is out there? So there was legacy hydrographic surveys. So basically, people have been going out for hundreds of years, measuring the depth and taking a sample for anchoring points. So there's a wealth of this information. The problem with this is it's traditionally in low energy sites, so you wouldn't want to anchor your boat in a whirlpool or something, so you have no data from those sites. And then there's biological surveys, which are also really good, but tend to be near the shore since it's diver collected. But if you put these together, you do sort of get a fuller picture of the area. And here's an example of some hydrographic data where these like SSH and M for muds are all over the place. So we took all this data and then normalized it into the 5 folk, and then we could use that to model the spatial distribution. The second approach was using high resolution multi-beam and backscatter. So backscatter looks like this, where it's just the harder the substrate, the greater the reflection, so you can work out basically mud, sand, rock. It's a lot better way of doing it because you actually just have you can actually draw around areas, and it's actually that, it's not a model, this is here. The problem with this is you can't get to the coast, the white ribbon effect. Ships doing this can't get too close, so there's always a gap. So the third method was throw everything together and see what comes out. So we did this over all the Scottish fjords, but this is an example from Loch Linnhe. We can see that this is the legacy data, just the point data, and we get a fairly good coverage of most of the areas, but you do see that some of it's quite geometric from the modeling, and that's just a factor of sample density. This one is the backscatter converted, and you can see there's white areas around the edge and there's bits just missing. So if you put all this together, we can get a reasonable and robust estimation of different sediment types across the system. We did this for all the fjords. The simplest one we could do to every fjord, the backscatter there's only backscatter available for about 30 fjords. And so it is not a complete data set, but it's as good as we're going to get. And we did a pilot sampling, got bulk density data and organic carbon data for the different sediment types, and basically applied that. And as you see from here, the muds have the most, the sands and rock of the least, which is not a surprise. But we did this for Scotland and Ireland, and basically the top 10 centimetres of sediment in Scotland hold about 4.16 megatons of organic carbon, and Ireland is about half that, but they've got far less fjords. So the next thing is, okay, we know how much carbon is in these systems. How quickly was it buried? So we went out in pre-COVID era on a summer holiday, basically, and got cruise around the west coast of Scotland and collected a pile of multi-cores to get burial rates for Scotland. It's always been just no data for this from Scotland, which is always hampered global estimates. So we went and collected all these, and we got radiometric dating done, lead to 10, cesium, americium, and some radiocarbon dates, and worked out organic carbon burial rates. So, and we did some isotope mixing models to work out where the carbon comes from. So you can see from this plot up here, this is the OCR rate, so the organic carbon accumulation rates we measured in the cores. So the blue is the global average, and the dotted line is the average from our fjords. So you can see that the Scottish ones are a lot higher. And it was a bit confusing because in my head, I was thinking there's not as much terrestrial carbon in the Scottish systems as someplace else, some other places in the world. So I was thinking it was going to be lower. You can see that from this, where the OC tail is actually a lot of them are lower than the global average. There's a few that pop out, but not everywhere. So what's driving this higher OCRs in Scotland? And is it, if it's not terrestrial, does it mean it's the marine input? So yeah, before we get to that, I guess this is the OCRs we got. And when we actually calculated it, basically Loch Eriboll, the third largest fjord in Scotland, buries the most out of the ones we measured, which is not a surprise. But we took this, we instead of what normally would happen is we take an area coverage of fjords and multiply it by the average. We actually use the spatial distribution of the carbon, or the spatial distribution we worked out from before, and focus on what we know. So we know about 40% of the Scottish fjords is mud. So we have a burial rate for mud. We upscaled. We had a burial rate for mixed sediment, and we had an area for mixed sediment. We couldn't core sediment, so we don't have anything for that, and it's still quite a large area. So we don't have any data for 505 kilometers squared of the Scottish fjord seabed, but the ones we do know bury about 84,000 tonnes a year, and it ranges between about 50 and 100,000. Which is, if you think back to what I said about the North Sea, so the North Sea buries 100,000, and essentially these fjords bury the same amount, but the North Sea is 190 times larger. So these systems are really outperforming any other local marine sedimentary system. And what we think is driving a lot of this is marine input. So we asked the question, are these systems driven by marine input or terrestrial input, like many of the other world fjords are? So we collected samples from all over Scotland's fjords. We measured isotopes, organic carbon, and just did simple mixing models. And we basically found that most of the samples came out about 0.4 or 40% of the carbon was terrestrial. So 60% is marine. And it's like, okay, so there's clearly more marine in our systems than has been observed in Chile or New Zealand. So we thought about it, and Joe Faust and Joachim Nies came up with this conceptual model of fjords that looked at how much the input of freshwater and marine input over the sill, how different ratios of that can drive how much the mix of organic carbon in the systems. We basically found that we think the majority of Scottish systems are this model, so the D. So they have a high input from the marine end because our sills are not massively restrictive. They are there, but they're not, some of them are quite deep. And in general, though you would think Scotland's quite wet, the runoff into these systems is fairly small. So this is the sort of model we are thinking about. So we took that idea and went, so how do we use the data we have and some of the geomorphology knowledge of these systems to try and come up with a model to estimate the terrestrial carbon in systems we don't have anything. So we went back to, okay, the outer sill depth probably controls the marine input. So it's probably a good place to start. We tried this on a few things. This is the one that actually came out well. So we took all the data we had, plotted against outer sill depth, and there's a fairly good relationship. So basically, the deeper the sill, the less terrestrial carbon the systems retain. So we used these models to just calculate across the Scottish fjords how much organic carbon was there, or how much terrestrial organic carbon was there. And you can see that the FTER, so the dotted line is the mean for the actual measured fjords. The solid line is the modelled one, and it comes out about 46% of the carbon is terrestrial if you in the model, and it's 36 if we look at the measured systems. And if we think about the global average, it's 52 to 66. So our systems are way more marine dominated than the global average. And we start to think, are ones slightly weird, or the ones that have been measured before weird? And we actually found that some of the Norwegian systems are coming out the same. So this is work by Fausten Nies in Trondheim Fjord, and they're plotting OC, the marine contribution, and you can see that in some places the marine contribution is above 70%. Trondheim Fjord is a bit more of a mix, but it seems these systems are as open as the Scottish ones, and we're seeing similar patterns, which is good for us. So basically the Scottish systems, the high OCARs, we think are being driven by high marine input. So when we think about this source to sink, we actually have to start thinking about the source as well. Most of this will be focused on the sediment. So using some European soil erosion models that were developed in the mid 2015-ish, these are driven by rainfall and water erosion, not wind. We combine this with the Scottish topsoil organic carbon map, and we can get to a number of soil carbon loss per year, which is the blue map. So annually, we calculated about 5 megatons of organic carbon is mobilized from these catchments. Not lost is probably the wrong word. And if we assume, using some of the literature, about 10% of this actually reaches the fjord, that comes out about 500 and about 500,000 tons. And if we use the burial rates per year of the actual burial, we basically estimate about 10% of the carbon lost from the catchment is trapped in the sediments. So the real question is, where's the other 90%? Well, some of it might be exported through the fjord out to the open ocean, which I'll talk about a bit later, or it's never actually, some of this carbon has never actually reached the fjord. It's been remobilized in the catchment and deposited in the catchment in a floodplain. So this is not an exact science. This is quite rough, but I think it's a good start to think about these transfers. When we bring all this data together, we can actually start to get to an OC budget for Scottish fjords. So we have a rough input term. We know the burial, we know the storage. So we have all that. The real questions now are basically the actual processes that control all of this, and how much is being exported offshore and how much carbon is being imported from marine sources. So these are still the big questions is on this end of the factor in Scotland anyway. So that was basically the overview of the big picture stuff. And now I'm going to go into a bit more detail about different things. So one of the things we want to know is how do these stores develop through time? So this was a collaboration with Tom Bianchi. And we looked at before I started my PhD, a core was collected from Loch Sunart, one of the bigger fjords, a 22-meter core that reached back just 8,000 years. So it's very high resolution. We decided to focus on the top 1,000 years to look at how anthropogenic pressure has changed the sedimentation and carbon input during that time. So we did the standard geochemistry, so organic carbon, delta 13C, we measured organic matter and some ICP-MS to work out local factors. There's mines in the area for copper, lead and zinc. So we looked at all these things. And we basically found, using this simple approach, that for the vast majority of the last 1,000 years, everything was fairly stable. But around the 1600s, basically all hell broke loose, and the amount of terrestrial carbon entering the system massively increased from about 5% of that at the core site up to about 30%. So a massive amount of terrestrial organic carbon entered the system. We looked at this further with biomarkers with Tom, with the bit index, some fatty acids, some alkanes, and they all show the same picture. Fairly stable, then a massive input. And we did some bulk dating on the system, on these sediments. And when we see the large input of organic matter, the age offset between the organic matter and the shell age increases to almost 1,500 years. So there's a lot of old carbon entering the system at this point, which suggests that the erosion and soil loss is taking deep soil that was trapped in the catchment long ago. We attribute this mostly to deforestation that made the catchment more susceptible, and the potential way this is linked to the NEO, which switched at the time into wetter conditions and might have triggered the massive amount of carbon transport into the fjord. So that's what a fjord in the middle of Scotland. We're currently working on another big core we managed to collect during the COVID pandemic in Loch Eriboll. So the most northerly fjord in Scotland, the one that points basically directly up to the Arctic. And we've done some initial, we've got some initial dates. It's about the core's about 5,000 years old. And what we found was there's a massive disturbance in the middle of the core. There's nothing on geophysics. So something has happened basically between 150 and 100 centimeters. Something's happened. I've got a feeling it's a submarine landslide within the fjord, but I'm currently not sure. I originally thought it might have been the Storegga landslide in the North Atlantic caused this, but the dates are wrong. But unlike the last, like this work with Tom, where we used biomarkers, this time we're using pollen to understand the catchment responses. So I've got a colleague at St Andrews who's working on this, and basically this is still a work in progress. But basically you see the trees dropping quite dramatically and the carbon goes up, which is good. Well, it's not good for the world, but it's good for, it sort of backs up my ideas. The other thing we notice is the amount of damaged pollen grains in the recent times is massively increased, and damaged pollen grains are a measure of transport. So there might be a lot more soil actually coming into the system currently than before. So this is just something we're working on, but this did raise questions about aged organic matter or aged carbon in systems. So most of Scotland's west coast is metamorphic or igneous, so there shouldn't be much fossil carbon, which this diagram shows basically the OC petrol, the percent of fossil carbon is basically 0 in the west coast fjord sediments. The north coast, where Loch Eriboll is, there is some sedimentary rocks, and we do see some potential fossil carbon input. But on the whole part, these systems shouldn't just be biospheric carbon. So we can start to think about the transport of old carbon in these systems. And if you look at this, this is bulk 14C. The orange blobs are fjords. The green ones are continental shelves just outside the fjords. And we can see that there's quite a lot of difference. So the continental shelves samples tend to sit between about 150 and minus 150, minus 200 for delta 14C. What we see in the fjords is a far larger mix. We've got modern, we've got very old. So the two very old samples with a lot of carbon, we believe comes from peatlands in the upper catchments. We basically think we sampled a chunk of sediment with a lot of peat in it, and it's ended up being very old with a lot of carbon. And the modern stuff, it could just be modern carbon, but it could also be related to aquaculture. So we do have to think about these factors a lot. So to extend this work, I started a collaboration with Tim Eggleton's group in ETH in September, where I collected surface samples from the top of cores from across basically every North Atlantic fjord system. And we measured radiocarbon on them and a pile of other proxies to work out what's controlling this. So this is still a work in progress. So these two plots, I've basically taken out the glaciated systems because they're so different from the vegetated systems. But you can see here, so the red is Norway. And these are by far the deepest fjords I've ever sampled in. So some of these got very deep. And they tend to hold basically the oldest carbon. The Scottish stuff is spread over a bigger area. But again, this is basically the peatlands driving this, and there's a lot of modern. The Faroe Islands is basically similar to Scotland, which is not a surprise since basically the Faroe Islands and the Shetland Islands are very similar. An interesting one is the green, which is Iceland. So basically all of it's modern. It's all brand new. There's no old carbon in these systems, which is, you wouldn't think there's fossil carbon. It's all volcanic rock, so that's not a problem. But you would think there'd be terrestrial carbon. And recent isotope analysis basically puts, we've got 150 samples. I think the most depleted delta 13C value we got from Iceland was minus 22. So it's all marine. And talking to people, there's a large contingent of palynologists and environmental archaeologists at St Andrews, and they suggest that there's not actually, in some of these systems, there's not actually any soil to be eroded. When the Vikings arrived, they basically chopped down all the trees and the soil's long gone. So anything that is going in is basically modern, and it's probably there's not much soil to enter system. So that might explain that. So this again is ongoing work. One of the things I'm really interested in is we sort of look at these systems in like absence of the wider ocean. So yes, a fjord is an excellent sediment trap, but some of it has to get out. So over the last couple of years, we've been collecting a lot of samples from this area. So this is the Firth of Lorne. There's a lot of fjords here. This is the biggest fjord complex in Scotland. And then we've collected surface samples all the way across. And we basically do an analysis, every analysis we can on this to try and work out how it's all connected. So if you actually do all these analyses and throw them into a cluster analysis. So I got this idea from Tessa Van Vroot, who was part of Tim Eggleton's group and is now in Holland. If you do this, you can actually see that the cluster analysis identifies a couple of areas or 5 areas. And in general, they do make sense. So the orange areas are the hypoxic fjords. So the upper basin of Loch Eriboll and this little one over here. The purple tends to be the upper basins of fjords or quite restricted fjords, and then the green and blue are transitional systems. So transitioning out of inshore to offshore, and basically the red is sand. It's like proper offshore deposits. So when you do this, you can sort of identify different zones of the local area. And this could be useful for if you want to manage these systems or a number of other things. But yeah, and these are basically the outputs from this. You can see they are different systems. And yeah, if you look at the particle size data from across this, you can see the red offshore area is essentially sand. And as you move inland, it becomes finer and basically more muddy, which is what you see. The last thing I really want to talk about is carbon reactivity. So recently, there has been a lot of publicity, research, headlines about how basically we're all doomed because of bottom trawling. So there was this paper that came out by Sala, and it's caused, let's be honest, a lot of controversy in the world. There's a lot of people out to get it. I'm not one of them, but I think there is issues with it. And some of the reporting, like the Guardian saying bottom trawling releases the same amount of carbon as air travel, is a bit mad. So one of the things I was working on before this came out was thinking about the reactivity of the carbon. How is there a simple way to understand the liability, how biodegradable it is, how likely it is to be lost as CO2 if disturbed? And we have a thermal gravimetric analyzer, which we can basically put samples in, combust them, work out weight losses at different temperatures, and these can be attached to different lability classes. So labile, recalcitrant, refractory. So we did this. So in the Sala paper, they say global sediments, 70% of the muds are 70% of the organic matter in mud is labile, 28.6% of organic matter in core sediments is labile, which seems extreme at the best time. So we measured this in Scotland. So this is a composite of 800 samples. And basically, even in the fjords, we didn't really see 70% of the organic matter being labile. The highest we saw was the low 70s, but we also got stuff down at like 18%. And when we get offshore, and offshore is really what this paper was talking about, 20% of the muds, the organic matter in mud is labile, and even less in core sediments. So the actual outputs from this project of saying it's the same as air travel might be wrong, because the carbon that is stored in a lot of these systems is so refractory that even if disturbed, they're likely not going to be released. Or if they are, it's only going to be a fraction of it, not all of it. So we came up with this carbon reactivity index, which is basically a ratio of the labile to the recalcitrant refractory material. And you can see what a basic conceptualization of it. And when we plot it against like proximity to land, you can see basically after you're about 5 kilometers off land, everything sort of normalizes. This might be due to this degradation, transport times. It takes a long time for this stuff to get out to the final deposition zones. In that time, everything sort of becomes degraded to the same point. So I'm not saying that bottom trawling, if you disturb it, bottom trawling won't do anything. It will, and it's damaging biodiversity and everything else. So if you wanted to focus on banning it or managing it, biodiversity is probably the better way to go than focusing on the carbon like is currently happening. But I think this is quite an important step forward, just to highlight that not all carbon is equal. And this is what we really have to understand going forward is, okay, we know there's a lot of carbon. We roughly know how quickly it's buried, but what is it? What is this carbon? And does it actually provide any climate service? And that is me. Nope.
Craig, thank you so much for this very interesting, wonderful talk. So let's see, if you have any question, our audience, please go ahead, unmute yourself, ask Craig directly.
Hey, Paul.
Yeah,
Can
go
I
ahead. Hey,
Hi.
Christoph.
How you doing?
Yeah.
Yeah, nice talk, Craig. Thank you for the talk. I have one question regarding the one thing you didn't talk much about is the recycling, the mineralization of organic carbon, either from land or from the sea. So that's one. At some point, you said like you can account only for 10% of the terrestrial organic matter which is deposited. Do you think that mineralization can account for some of the non-accounted for carbon in the fjord system?
Yeah, I think that is an important missing part. So especially in these Scottish systems, which are quite well oxygenated in comparison to New Zealand, which is quite hypoxic, these systems have a lot of oxygen. So there's plenty of opportunity for this stuff, the organic carbon to be remineralized and just transported through these systems. So yeah, in that budget, I basically said there's all this cycling going on in the middle, and it's still the part we really don't have a handle on. But I think, yeah, it probably plays a big part in that missing carbon.
Okay.
So Greg, is any PCO2 matter, in the surface of water?
There's probably some data from around one of them, but it's not been done in any sort of.
That would be interesting to see how much they burned off.
Yeah, there's also, I think, there's a lot of missing things. There's a lot of methane floating around these systems as well.
Oh, okay.
Just from coring, we've cored, and then the caps of the corers popped off with methane. So there's a lot of gas floating around these systems.
So if you run the chip, the seismic, basically you can get a curtain.
Yeah, so on that seismic I showed, there's patches of gas in the that we've identified. So there's a lot of gas floating around.
Cool. So anybody? Sophia, you have a question?
Yeah, hello. Hi, Craig. Thanks for a very nice talk. Yeah, I think that's really interesting, and that's mostly the fjords you are looking at are marine dominated, right?
Yeah.
So I'm guessing that there is very little evidence for terrestrial sources, but we also see evidence for terrestrial sources in other types of fjords. For example, the ones we study in Canada or others in New Zealand or Chile. So how many types of fjords do you think there is in the world, and how does fjord type influence the carbon cycle, whether it's more marine or terrestrial? Is it going to return faster to the atmosphere if it's marine or terrestrial? I guess there's many types of fjords.
Yeah, that would be my answer. It's like, I don't know how many types there are. So even in Scotland, I would say there's a couple. I say like my overall guess is Scottish systems and the Western Norwegian ones are similar.
Right.
Once you get more, basically the glaciation was more extreme, they change again. The Icelandic ones, the data that's coming out there is, they're just weird as far as I can work out so far. They're just very strange. The Greenland ones are probably different again. Yeah. So I think it's basically, there'll be so many different kinds. I think the marine ones, the marine carbon is more labile.
Right. Okay.
It will be burnt off quicker through oxygenation and just the processes. So if you start thinking about the carbon burial as long-term climate regulation, I don't know if these marine ones are worse, because the stuff that's actually going in will probably be remineralized quicker than the terrestrial ones, especially such as New Zealand, which is basically hypoxic most of the time and anoxic a lot. That stuff's basically not going anywhere. In our systems, it's a lot more biogeochemically active, I guess you'd say. The stuff, it's releasing carbon as well. And we've all sort of just focused on the carbon going in and not really thought about carbon going the other way at the moment.
Yeah, okay. And just a second question on that matter of reactivity. So I really like your new work, which I just saw in GRL yesterday, but I didn't quite get to read it yet. So how do you measure reactivity, whether carbon is labile or refractory? How do you get to that physically?
So we took a really simple approach. Well, we started off trying like FT, IR, and pyrolysis, GC mass spectrometry and stuff to do all this, and it was working, but it's really expensive, so you can't do it at scale. So we have a thermal gravimetric analyzer, which is basically posh loss of ignition. It's a balance inside a furnace that weighs and you ramp heat it and you work out a mass loss. Okay. And there's some work being done out of Newcastle, which has temperature ranges for labile, recalcitrant, and refractory. So if it's lost between this one, it's labile, this temperature. So it's not, I'm not saying it's the perfect method for doing it, but it is a good method for basically a cheap and quick method for doing it over large areas. And I think that's what we sort of need first, is basically, what is this stuff? And then we use it as basically what I want to do is take that data and now look at it and target specific stuff with the fancier techniques.
Okay, thank you.
Yes. So, Craig, some very interesting basic info background. Is Scotland any glacial or any ice melting water discharge to the void?
So no, I think the last bit of ice left Scotland about 11,000 years ago.
Oh, okay.
It's all our systems are vegetated. So
I need to visit Scotland. So anyway, so the question followed by compare. I know you work on middle latitude. Compare those with a little bit high latitude. With the still ice, discharge.
Okay, yeah. So the systems of Scotland are quite often compared to Svalbard, as like Svalbard was a analog to what Scotland was 13,000 years ago. So yeah, we've got a number of samples that I haven't shown in this about Svalbard, about the age of the carbon up there. So the carbon coming off those fjords are really old because sedimentary rocks, coal, Svalbard is basically a massive deposit of fossil carbon, which is all pouring into the glaciated fjords. But yeah, glaciated fjords tend to have much higher organic carbon burial rates than vegetated systems, basically because the glaciers are just basically processing rock and throwing it in. So it's huge. They have huge burial rates, but the organic carbon is basically fossil carbon. So actually moving it's quite bad for climate. If that weathers, it's a lot of carbon that was stored a very long time ago getting released. In the Scottish systems, it's all biospheric, it's all biological material that's going in, either marine or terrestrial. So the rates are slower, but the actual capture of that carbon is beneficial to long-term global climate regulation, opposed to the huge numbers in the Arctic, which is not really doing anything, just moving carbon, just moving rock from one place to another.
Okay, very, very nice. And anybody else? Yeah, okay, I do have a proposal pending on the Greenland, the Fjord. If I get founded, I will get enough sample I can share with you guys.
Okay, perfect.
Yeah. Okay. So anybody else? Any questions? If no, Greg, thank you very much for a very inspiring talk, and so appreciate. Okay. Yeah.
Okay.
Yeah. Okay.